Hello everyone, welcome to Nevin's Data Lab. In this video, we will learn about PCA or Principal Component Analysis. Principal Component Analysis is an unsupervised learning algorithm and it is used for dimensionality reduction. So let's say you have a data set which has like 1,000 columns. Training a model on such a data would be computationally very expensive. So we aim to reduce the number of columns without losing much information on the data. That is where we can use PCA. So let's say you have a data like this. So basically, if you want to understand it in a simple way, you can think of it as moving the axis instead of the data in such a way that the origin lies at the mean of the data and the direction of the axis would be in such a way that it would explain the maximum variance of the data in minimum number of axes. Like let's say in this figure, you can say in one axis itself, the majority of the data variance is explained. Like the variance would range from here to here. While in the second axis, the variance is very low, that is from here to here. So you can see that one axis itself explains majority of the variance of this data. So what are the steps to do that? So first we subtract the mean from x to get the origin to 0. Then we calculate the covariance matrix of the data to itself. And then we calculate the eigenvalues and eigenvectors of this covariance matrix. So what do we get by that? We get the eigenvectors, that is the direction of this axis, and eigenvalues, like larger is the eigenvalue, the more is the variance explained by that axis. So eigenvalue of the corresponding eigenvectors basically explains the variance of the data explained by that particular axis. And then we will sort them in descending order and then select the first k. Like let's say we had 10 columns and we calculated the eigenvalues and eigenvectors and we selected the first two columns and first two eigenvalues. Then that is basically we are dividing a 10D graph, 10D data set to a 2D data set. So that is where dimensionality reduction comes into place. So let's start with the code. So like always, let's start by importing NumPy as NP and then create a class PCA. We would need the init function. We would need the fit function. And we would also need the predict function, but instead of predicting we are basically transforming over here, so I'll just write it as transform. So let's start with the init function. For the init function we need the n components, that is basically the amount of and basically the value of k, basically how many dimensions we want to reduce it to. So self.n components, and we'll also write the mean and initiate it to none. This is basically for calculating the mean of the data. Next we'll go into the fit function. So for the fit function we need x, and we'll set our mean to np.mean x along axis is equal to 0, and then we will also make the mean of the data to 0. So how we can do that is we can just subtract each point with its mean. Next, if we look into our steps, we want to calculate the covariance of x given x, so that can be done by np.cov x transpose, because basically the function expects column data instead of like in row format. And next, if we check, we want to calculate the eigenvalues and eigenvectors. So eigenvectors from eigenvalues can be directly calculated by n.eig of covariance matrix, and this eigenvector would be calculated in a column format. So but for easier calculation we can convert it to like row format, so we can just do its transpose. Next, if you see, we have to sort them. So for sorting we can get the indexes as np.argsort. Like I said in the previous video, argsort basically sorts it and gives the indices of the sorted list instead of the values. So that's why I've written indexes over here. And we can sort the eigenvectors and then reverse it because we want the descending order. And we can sort the eigenvectors and eigenvalues like this. So next we can see that we have to choose the first k eigenvalues, that is the first n component eigenvalues. Let's just store it in a variable called components. We can just set it to none initially and do self dot component is equal to wait, we have to sort this based on the eigenvalues, not the eigenvectors. And then we have to get the top k eigenvectors, that is self dot n components. So that's it for the fit function. Now we can move on to the transform function. For transforming, we basically have to like project the data, so we can again like center it towards origin. So and then we can simply return np dot x comma self dot components. We would also have to take the transpose of this so that the dimensions are correct. So that should be it for the code. So if everything works perfectly, we can see that the dimensions would be reduced. So let's check that with a sample code. So like in the previous video, in the previous code we can import the accuracy function. We can also import this part. Actually, till this part we can import and we can copy. And instead of the breast cancer data, let's start with the iris one. And let's see. Actually, we don't have to like split it because we are not like training anything. Let's just fit it. Let's call PCA first. PCA, and let's get the let's get only like first two dimensions. So this would be PCA dot fit. As you can see, we have only defined, we only need the x argument like the data, and PCA dot transform. Next, we can store this into PCA final, and we can like print the shape of the PCA final, and we can also print the shape of x to see the difference. Let's run this. Okay, we have an error over here. Let's see. For transform also we need the x. That was the error, I guess. Let's run it again. Yep, we can see that we initially had like 4 columns. Now we have only 2 because we had applied this to 2. Let's say if we do this to 3, we'll get 3 columns. So that's it for PCA. Thank you so much for watching. If you do like this video, please like, share and subscribe. And also if you have any doubts, please leave them in the comment section and I will try to solve them. Yep, thank you.